Let's start this lecture by doing a recap, and I want you to keep in mind that max-min with no qualifying adjective will always mean global or absolute. If these word problems want you to find the most or the greatest or the maximum that something can be, they are talking absolute or global. Least, smallest, minimum, absolute, or global. We can easily handle the problems by making good use of the first and second derivative tests. Don't forget, you know the second derivative test as well as the first derivative test. Sometimes it might be difficult to test on either side of a critical point, but it's not difficult to find the second derivative and plug that critical point in. So do not forget that you know two tests in order to determine whether you're dealing with a max or a min. These max-min word problems that we've worked up to this point involve being given a function or an equation and finding critical points and using one of those two tests to see where the max or the min happen. For word problems, there are some additional steps at the beginning of the max-min process, and the one thing that I stress on every lesson, and most especially on these word problems lessons, is process, process, process. So here is a loose guideline, and I would say loose. Not every step has to be done on every problem, and not every step needs to be done in this particular order on every problem. This is a loose guideline in that if you check to see if any of these steps need to be done, then you have properly worked through your max-min word problem. The first thing that I would always do if it's not provided for me is I would draw a picture. Draw a picture and make sure that I label it appropriately and intelligently using variables that make sense. The next thing is I would try to find an equation that gives me a relationship between those variables and then identify which equation they want me to optimize or to find the maximum or minimum of. Remember, I am going to use the relationship equation or function to put the optimization equation or function in terms of one and only one variable. That's what it means by use the conditions of the problem to eliminate all but one of the variables. You are going to express this equation or this function in terms of one and only one variable, and you need to determine whether you have endpoints to your interval. Many of these problems, because they are contextual or applied problems, will not have endpoints to the interval. But that is by no means to say that none of them will. We could encounter a problem where endpoints do exist and do make sense, and a maximum or a minimum could occur at an endpoint. Once you have the optimization function in terms of only one variable, then differentiate with respect to that variable and find your critical points. Find your stationary points. Don't forget you have singular points as well. Don't just look for where the derivative equals 0. You might also be looking for where the derivative is not defined. You are most often looking for stationary points where the derivative equals 0, however. Use what you know about those two tests and identify whether you are dealing with a max or a min to verify you have found the value in question. We're going to work a few more examples just so you see different types of problems, and it is my hope that you will just get better and better and better at turning words into mathematics. So find two non-negative numbers. These numbers are going to be positive or 0. That's one way to write non-negative. These numbers can be any positive value or they could be 0. Whose sum is 9. That's turning that into an equation. And so that the product of one number and the square of the other number is a maximum. Now, we really haven't had an issue with our word problems up to this point as far as what to set them equal to. We've usually been finding max volume or, minimum surface area or something like that. I would warn you to be careful of saying, well, I want this product to be a max, so I'm going to call it M. Well, understand min starts with M as well. So I tell students to stay away from M. What I would rather you do, number one, you can set it equal to anything. You could say it was Z. It doesn't really matter. But it might be just as easy to call it P for product. So this product equation, I want completely in terms of one variable, and I like X. So it would be really fantastic if I could find a way of writing Y in terms of X. Here's the process for max min. Find your relationship equation. I see one right there. Find your optimization equation. There it is right there. That's what they want me to maximize. Use the relationship equation to put one variable completely in terms of the other. Use that to substitute into your optimization equation so that you can differentiate with respect to one variable. That's why it's a loose guideline. On this particular one, I don't need to draw a picture. There's nothing to draw a picture of. So let's clean P of X up so that we can take the derivative of it. 81 minus 18x plus x squared. That cleans up to x cubed minus 18x squared plus 81x. The derivative, 3x squared minus 36x plus 81. So we want to find where this equals 0 or does not exist. Again, this is a perfectly beautiful, well-defined polynomial function. Exists everywhere for any value of x. Every term has a 3 in it. So I'm going to factor 3 out. I believe 81 divided by 3 is 27. I need to factor and find my critical points. I need something that when I add it, I get negative 12, but when I multiply it, I get positive 27. I believe those are the values that would do that for me. So I have 2 critical points. I need to run a test just for argument's sake. Instead of running the first derivative test, and I'm going to go back to that, let's run the second derivative test. When I plug the critical point of 3 into the second derivative, I get a negative value. That tells me that P is concave down and that x equal 3 produces a max. Let's do P double prime at 9. 18 minus 12 yields a positive second derivative. Tells me P is concave up. X equal 9 is a min according to the second derivative test. The question says the product of one number and the square of the other number is a maximum. So that is going to happen for me when x is 3 according to the second derivative test. So when x is 3, y has the relationship of 9 minus x, so y would have to be 6. Here's the relationship that I'm using. So find two non-negative numbers. I would say the non-negative numbers are 3 and 6. They do have a sum of 9, and we are guaranteed, because of the second derivative test, that the product of x times y squared will be a maximum. So this illustrates how the second derivative test is going to work for us for max-min. We can use it just as well as the first derivative test. It also illustrates why the steps that I gave you before are a loose guideline. We don't need to draw a picture on this particular problem, but we did need to find the relationship equation or function and the optimization equation or function. The rest of the steps we applied. We did not talk about endpoints. This would be one of the rare cases where, since I wrote everything in terms of x, I'm looking for an x interval. The interval in which x needs to lie does have a left endpoint. The words did tell me that x could equal 0. This relationship tells me that the biggest x could be is 9. This also illustrates that we could have a closed interval. What is interesting is that when we do have x equal 9, we have y equal 0. And the maximum of that product would be 0. That's kind of trivial. When x is 0, the maximum of this product would be 0. So an argument could be made that in the context of this problem, x equaling 0 or x equaling 9 is not going to give me the optimization I'm after. However, they didn't say they were non-zero values. They said they were non-negative values. So we would have to explore what was happening at 0 and 9 for x. Let's work an additional example. A wire 50 inches long is cut into 2 pieces. So we have a wire that is 50 inches long. It's cut into 2 pieces. Let's say here is the cut. One piece is bent into a circle. The other into a square. Where should the wire be cut to minimize the sum of the areas of the 2 shapes? So we want, here is the area of a circle, we understand is pi r squared. The area of a square we understand is side squared. We understand that the perimeter of these 2 figures added together, which is circumference of the circle and 4 sides of the square, can be no more than 50 inches. That is going to be the relationship function. That is going to give me a relationship between r and s. The optimization function is they want me to minimize the sum. I'm going to use s, and they want me to minimize the sum of the 2 areas.